Well, thank you for the introduction. That was nicer than expected. And thank you for the organizers for inviting me to such a wonderful conference. So I would like to talk about joint work with Harry Bray, the Canary, and Nyima. They're here, the last two. And so what I want to do is give enough definitions to get to the main result as quick as possible. And thanks to the wonderful mini courses, my job is much easier, okay? So we've seen flags. I know there's a lot of text here. We're going to go step by step. But it was good to see it all at once for this slide. So we've seen flags. We've seen flags in generic position. And I want to add a little definition in this context that it's very important in higher rank technical theory. So I want to first define a concept from linear algebra, which is the concept of a totally positive upper triangular unipotent matrix. So this is a matrix. It's unipotent, so some of these minors are going to be 0. But the ones that don't have to be 0, I want them to be strictly positive. So for instance, 1, 2, 0, 1 is an example. And then 1, 3, 9, 0, 1, 3, 0, 0, 1 is not an example, because I have this minor where the 3, 9, 1, 3 minor is 0. Okay.
Do you know how to use the pointer?
I do, but my hands. Yeah. Okay. Okay. So a concept for if I take a tuple of flags in generic position, I'm going to define what it means for these flags to be positive. And let's look at the example first. So if I have points in RP1, which is the space of flags in R2, I can ask for them to be cyclically ordered. And so in a higher rank, there is a very powerful generalization of this concept, which is the concept of being positive. And so if I have two generic flags, let's say the first one, F1 and Ft, they are in generic position, so they define a line decomposition of Rd. Okay? So I can pick a basis adapted to this line decomposition, and now I can talk about totally positive matrices with respect to this line decomposition. And so I want these flags to be related by this totally positive, applying totally positive matrices sequentially. Okay. But so the main takeaway, we're not going to use this concept very much, but I need it for a main definition. But think about cyclically ordered points. Okay? Okay. Who are the protagonists? So I want to start with a surface that has at least a puncture. Okay? So surface of genus G, I want to have at least a puncture, and I want to assume that this surface has a finite area hyperbolic structure. Okay, so I have cusps, one not. So in particular, the other characteristic needs to be negative. And now a cusped Hitchin representation is a representation of this gamma, which is the group, a subgroup of PSL2R, into PSLDR, with one of these very nice maps that we've seen throughout the conference, okay? And what I want this map to be rho equivariant and continuous from the limit set of gamma to the space of flags in Rd. And I want this map to be positive, meaning that I have a notion of positivity in RP1. I want that to be preserved when I do this, when I apply this map. And these positive representations are very well studied objects. So for instance, for d equal to 2, these are finite area hyperbolic structures on the surface. For d equal to 3, Ludovic Marquis proved that this coincides with finite area convex RP2 structures. These representations are not Anosov, but they fit in the framework of geometrically finite Anosov subgroups. So they were studied using positivity by Gonchar for 15 years ago. And a lot of people in this room are very interested in these representations. I'm going to single out the paper of Canary Zhang Zimmer, the work of Canary Zhang Zimmer, because it's not going to appear explicitly later on, but it's in the background of a lot of things I'm going to say today. Okay? Yes?
So is it different from, you could embed gamma via the irreducible representation and then think about the continuous deformations. Is it
as the same thing? It's the same thing. It's the same thing. Yes, that's actually. So if you've seen the definition for a Hitchin representation from earlier, these are continuous deformations of function groups of uniform lattices, and these are continuous deformations in this larger character, right? Yes.
You got to deform preserving the joint block structure of parabolics. Yeah.
I'm restricting myself a little bit just to make things a little easier. So you need to, as Dick said, you need to be sure that you don't ruin the puncture.
Okay, parabolic goes to parabolic.
Parabolic goes to parabolic, exactly. Okay, thank you. Okay, so if you're an expert on this kind of stuff, please check your emails for one slide. So I want to give a concrete example. This part is not going to be useful for anything I said later, but these are very concrete objects. So I want to kind of give a small example. And I'm going to take the smallest surface that I can think of, a tripuncture sphere on the left. And I'm going to take SL3R. So now I can think of this tripuncture sphere as being formed by two triangles. And this tripuncture sphere comes with a triangulation with vertices at the punctures. And so for Goncharov, associate to such an object invariants of pairs of flags and triples of flags. So every time I see an edge, I see two flags. And every time I see three vertices, I see a triple of flags. And there are projective invariants associated to these objects. And the fact that we're cusped Hitchin, so this condition about the parabolics, can be determined explicitly in terms of these coordinates, if you're familiar with them. So I did the computation. I hope this is probably 90% right, maybe 95. But I think these are generated for all cusped Hitchin representations for this surface. And there is only one hyperbolic structure, finite hyperbolic structure on the tripuncture sphere, and that corresponds to A2 equal to T1 is equal to 1. Okay? So very concrete objects. That's maybe the main takeaway. Okay. These cusped Hitchin representations, again, are not Anosov, but they have very nice structure. So for instance, every time I take a hyperbolic element in gamma, and I look at a cusped Hitchin representation, I know that rho gamma is loxodromic, meaning has distinct eigenvalues of distinct moduli. And so I can do what Andres did and define length functions for such an object. So I recall that briefly. So I can take some functional on the Cartan subspace, which is positive on the open Weyl chamber, and then I can define a length function by taking gamma, applying rho, then applying the Jordan projection to record the eigenvalues, and then applying phi because phi is an element of the dual. And since I have parabolic elements, here I have elements of length 0. So I need to be careful. Okay? If you're not familiar with this, here are examples. So there is the spectral radius length, where I take the log of the top eigenvalue, the first simple root length, where I take the ratio of the first and second eigenvalue, and then the Hilbert length, if you want, the ratio of the top and bottom eigenvalue. Okay. So all these lengths generalize the hyperbolic length. Okay. If I take something as function and cusped Hitchin in PSLTR, this is the hyperbolic length, maybe up to a constant. Okay. Main theorem. So the main result I want to talk about is an orbit counting theorem. I take a cusped Hitchin representation. I take one of these length functions. And now I get a set of closed curves on my surface that have length at most t. And since I'm cusped, I need to make sure that I don't count things that have length 0, like things in the cusp. And this set, as t goes to infinity, grows precisely like e to the delta t over delta t for some positive number delta that we prove exists. Okay? So this orbit counting theorem has many predecessors. I'm not going to be able to cite them all, But for instance, for closed surfaces, there is a early work of Huber, Margulis, Bowen. Maybe a comment for the experts, we do not use Margulis' strategy to prove this theorem. We actually use a strategy due to Lally. We generalize a strategy due to Lally to prove this theorem. When I look at an Anosov representation of a closed surface, this is due to Sambarino.
Isn't there... Did Sambarino get rid of the constant ever?
Which constant?
I thought there was in the quantitative representations paper, isn't there a constant that you have, or no? Am I wrong? Is Andres here?
I think the constant occurs when you count with the Cartan projection.
Okay.
This is counting with the Jordan projection.
Okay. Again, thank you, collaborators. Okay.
And so maybe not in this generality, but there is work, for instance, on ping-pong groups and hyperbolic surfaces by Dalbo, Peña, and Theorem. I don't know how to say that name. Okay.
But for Anosov subgroups with respect to minimal parabolic, I think Chow and From also proves this.
For cusped or non-cusped?
Non-cusped, I mean, but
okay.
Anosov with respect to...
Sorry, Mikey. Sorry, I'm just sorry.
I have a question.
Yeah.
Is it important that your linear form is positive on all of the Loesch-Weber, or can you just take like positive on limit cone?
Positive on limit cone is enough, but I wanted to be more. But thank you. Yeah. And sorry. Thank you and sorry. Okay, so Chow, and maybe I should write it. The second. Okay. Thank you. Okay, main result stated, end of talk almost. So I want to give a very rough idea of the proof, okay? And then we go from there. So the very rough idea of proof is to translate this problem into a problem in symbolic dynamics. So we have a hyperbolic surface that comes with a geodesic flow, and we want to look at the Bowen-Series coding, maybe of the recurrent portion of this of the geodesic flow. And the punctures are going to make life a little harder, so we're going to do a modified version of that. Then once we do the first step, we're going to be in the realm of symbolic dynamics, and we're going to actually look at some nice countable Markov shifts and that code this geodesic flow. And the first 2 points are about really one hyperbolic structures, but we want to do things for all Cusped Hitchin representations, so we're going to need to define some nice potentials that capture the length functions of different Hitchin representations. And then at the end, we're going to have an orbit counting theorem for this class of shifts and potentials, and it's going to apply to the setting. Okay? If I look at this slide and I'm in the audience, there are too many nice, there is some scary words, at least for me, but we're going to work on that. Okay? Questions? I typically go too fast, so
I put myself to line.
When you say countable Markov shift, you mean not finite?
I mean countable alphabet. So Markov shift come.
The shift space can be.
Yeah, sorry, countable infinite. Yes, thank you. Anything else?
Just so I'm clear, so that as opposed to a finite.
As opposed to a finite,
okay.
Yes.
So it's not a subshift of finite type.
It's not a subshift of finite.
Okay.
Yes.
Anything else? Okay. We're going to go through this. So I want to start with the Bowen-Series coding. I want to start with an example. So the idea, I have a geodesic flow, recurrent portion of the geodesic flow on an hyperbolic surface, and I want to replace this dynamical system with something symbolic. Symbolic maybe doesn't make sense right now, but you'll see. So let's look at the same example. So the tripuncture sphere. So that the triangulation I had before kind of gives you a tessellation of the hyperbolic plane. And now I'm going to forget about the green edge. I'm just going to have the red edges and the blue edges. So I'm going to get a fundamental domain. And I'm going to label each edge essentially by I'm going to label each edge by essentially grouping a word in the group, a generator of the group. So in the example, I can choose A that goes from one rank to the other, then A inverse, B, B inverse. And then if I look at a geodesic ray, starting from the origin, and I don't go straight into the cusp, I'm a little careful about that, then I can associate to that geodesic ray the labels of the edges as crosses. Okay? So somehow that gives you an infinite word in these letters A, and they're finite. Okay? So in general, what do? We take a fundamental domain for gamma with vertices in the boundary of H2, maybe it contains the origin, and then we get a finite alphabet given by the phase pairings of the fundamental domain. And then I can code rays using these cut-in sequences, keeping track of the labels. Okay? And we get a lot of this. So in this case, we get a finite shift. So we get a set of infinite words in this alphabet A. And I need to be careful that I cannot do A and then A inverse, so I get some translation relations. And the dynamic of the geodesic flow, actually, it's replaced by the dynamic of a shift. The idea is that I change fundamental domain, and so I get a right shift as a dynamic. So this is a map from the shift to itself. But we get a little bit more. We get maps from the letters of my alphabet into the group, think generators. And then we get a map from the whole shift into the boundary of H2, because I have a ray that's going to some point at infinity, so I can think of that point at infinity. And these two maps are somewhat intertwined. There's an equation. I get it wrong half of the time. The important thing is that here I'm intertwining the action of gamma and the action of sigma. Okay? But we get more. So actually, if I have a periodic word, if you think about it, periodic word means I'm going through this translate of the fundamental domains periodically. Okay? So somehow I get a group element that's the G of each of the letters in the period. And now I can look at a point at infinity given by x, omega x, and that point is exactly the attracting fixed point of this group element as an element of PS2R. Moreover, kind of a backward direction, if I have something that's hyperbolic, then I can find a periodic word so that gamma is conjugated to this gx1xk. Okay, so somehow this object is very good at keeping track of group elements, hyperbolic group elements at least. Okay. I'm going to quote Andres, even if he's not here. He said something I really liked yesterday. He said that if you want to use thermodynamic formalism, which we do, you need to feed it a nice dynamical system. And the long story short is that this coding is not a nice dynamical system where you have punctures. Okay? So we're going to need to modify a little bit. I'm going to leave mostly vague this statement, but I want to give a concrete issue. Okay? So this space sigma plus, this shift, is a metric space. What's the metric? I take two words. If they agree up on the first n letters, but then the n plus first is different, I say that they're distant e to the minus n. Okay? And so a little exercise is that you could check that this map that takes an infinite word into a point in the boundary H2 is not Hölder continuous in this setting. And I gave a hint. If you're stuck, there is a paper of Bray, Canary, and Kao on the pressure metric for quasi-function representations, in which they explain why this fails. Okay? So there are some issues, but there's also a fix. Okay? And so this goes back to work of Ledrapier against Stolbauer. The idea is that the problems come from the cusps. Okay? The problems come from the cusps. So what I want to do, if I go into a cusp, I wrap around, then I come back, come out of the cusp, I want to keep track of how I went there, how much time I spent, and then how did I leave the cusp. Okay? This is quite quite an involved construction, but maybe this is a first approximation of what's really going on. And once I modify my alphabet in such a way, I get a good dynamical system. I get all the maps that I had before, all these nice properties of periodic orbits and hyperbolic elements. The little drawback is that I need to add infinitely many words. Okay? So think about it in these terms. I need to keep track how many times I go around the cusp. So I can go twice, 3 times, 4 times, many times. Okay? Okay, so this is the setup, how to associate one of these countable Markov shifts to a cusped finite area hyperbolic surface. So maybe it's time for questions.
Can you say a bit more about this modified alphabet?
Not right now. Not right now. Not during not while I'm here speaking. But yes, I can.
Not in front of people.
Yeah, not in front of people.
Now she's going to get to the next section was talk.
Yeah. But I still the main theorem, so yeah. Okay. Other questions? Sorry, Bea. Okay. So this is one slide section. I want to reiterate what I mean by nice countable Markov shift. So I have a countable infinite alphabet. And now I'm going to be a little bit more precise here. What do I mean about translation relations? Transition relations. I just mean that some letters can follow other letters. And so I'm going to encode this by a matrix of 0, 1. And so look at sequences in a to the n. So the value of this infinite by infinite matrix is 1. So they're allowed to follow each other. And then I look at the right shift given by sigma. Okay. Maybe it's even nicer than this. So the countable Markov shift that we're looking at has some nice features that I'm going to define. They're called topologically mixing and BIP property. But don't be scared. So topological mixing just means that if I take 2 letters and I'm willing to travel for a long time, like depending on A and B, I can go from A to B. Okay. So there is an amount of time that I need to travel to go from A to B, but if I'm willing to do that, I can do that. And the BIP property, the way I think about it, is almost a compactness property. So in this countable infinite alphabet, I have a finite one, I have a finite subset, so that if I'm anywhere on my surface, I can get back to this compact part B in 1 step and get away from this compact part B in 1 step. Okay, so this maybe more precisely, oh, wrong button, spoilers. So I have a finite subset, so that for every letter, I can always find 2 letters in B such that I can follow B0 with A, and I can follow A with B1. Okay, that's what it means. Somehow, you should think of this as your surface maybe as cusps, but there is a compact part. Okay, and the idea is that these are nice countable Markov shifts, and their thermodynamical formalism is well developed, thanks to work of Omri Sarig and Moldin Urbanski and other people. And so if you would want to forget the meaning of these 2 properties, is fine. Just remember that nice means this kind of stuff. Okay, maybe I'm asking too many questions, but okay. Questions?
So can you say geometrically with the second property much again? So the first property means that you can ask the geodesic to do anything you want, basically, right?
Yeah.
Well, what the second property?
So that if I start here, I can go to the compact part. I mean, this is almost true. I can get back to the compact part in 1 step pretty quickly. And then if I want to go in a cusp, I can go from the compact part in the cusp pretty quickly, roughly. Okay.
Oh, and so it's just a like cutoff of how far you want to where you consider the compact part to start. That's how big the finite alphabet is. Finite subalphabet.
I don't think I know the answer to that question specifically, but sounds
You have to
right.
be a little more careful with what you just said.
Okay.
But yeah. Sorry, I'm doing a lot of sweeping. Okay, we have a nice countable Markov shifts. It's time for potentials, and the potentials are actually going to be related to what? Oh, I said 130. Okay, sorry, I got scared for a second. So the potential are going to be related to this Jean-François Canty Iwasawa cocycle that we saw before. Okay, so remember, I have a Cusped Hitchin representation. I have a length function, so that's what we had. And what I really want is to define a function from the shift to R that somehow captures the length function of my Hitchin representation. Okay, that's kind of the morally what I really want. Okay, and so there is a standard way to think of such a potential and associated to it a length. And the idea is that you take your potential and you take a periodic word, and what do you do to it? Well, I can look at f evaluated x, and then I can do one shift. I can do f evaluated as sigma x, and then I can do that as many times as the period. I add all those up, and this is somehow a notion of f length associated to such a function. And I want these two notions of length to match. So the one coming from the shift and the one coming from the Hitchin, I would like them to be the same. So remember, G is this map that takes letters in my alphabet to the group. Okay. So yeah, so this is a multiplication in PSF2R. Okay. And such a function exists. I mean, the construction is, goes back to many people. But maybe the first instance, I want to give the example, is the Bussmann cocycle. So let's think about the Bussmann cocycle for a second. So suppose I have I, and I have a point at infinity, which I can think of it as an element in my shift space. And now maybe I have a group element G. So G moves I somewhere over here. This Bussmann cocycle is the sign distance between these two orocycles, one passing through I and one passing through GI. Okay? And I can interpret that as saying, okay, G has some unipotent part that moves you, let's say, on orocycles, has some compact part that fixes I, and then there is this multiplicative, diagonal part that moves you along the axis between 0 and infinity. And so you've seen the Bussmann cocycle with values in R, but that's not right. It's in the Cartan space of SL2R. Okay, that's R. And so for a group element and a point at infinity, I can define a vector in the Cartan subspace. Okay. And so we can do the same thing in higher rank. It's a little trickier. Also, it's a little trickier that here I'm cheating a little bit and I'm picking my infinity to be a very nice point. Okay. But here's the construction. So the input is a group element and a flag. Now, if I have a flag, I can use an element of SOD to put it into standard position. So I can, this E1 is the standard basis vector, first standard basis vector, E2 is the second, and so again, I have a standard flag obtained that way. And so with a compact element, I can send Xi to Xi0. And then this Jean-François Canty Iwasawa cocycle is essentially the A part of the Iwasawa decomposition of G times K. Okay, so this is somehow tracking how you're moving in a specific flat in your symmetric space. So the Iwasawa decomposition takes GK and subdivides it into a compact element, compact part, diagonal, unipotent. And it's Gram-Schmidt when you're in SLD like we are. Okay, so you don't have to remember Iwasawa. Okay, so maybe the properties I want to know of this Iwasawa cocycle that are very nice. So the main property I want is that if I take an loxodromic element, this loxodromic element has an attracting flag. And if I look at Iwasawa of G with the attracting flag, I get exactly the Jordan projection. Okay, so somehow it's capturing the lens. And then here for fun, I also put the cocycle identity if you want to work it out. Okay, but the loxodromic part is important. Okay. Okay. So here come the nice potentials. So if I have a cusped Hitchin representation with this limit map xi rho, I have an element in my shift, which is, I can think of it as a geodesic ray. So the geodesic ray has a first element, which is an element of your group. So that gives me an element in gamma, gx inverse, x1 inverse, and I can apply rho to it to get an element in SLDR. And then this x gives me a point at the boundary of H2, so I can apply xi rho to that element of H2. So I take something in C+, I get a group element and then a flag, I apply Iwasawa, and then I apply phi. Okay?
So this is why you needed this to be locally Holder continuous.
Yeah, I mean, locally Holder continuous everywhere.
Right, yeah, because otherwise you couldn't do thermodynamic formalism.
Yeah. And this does exactly what we wanted to do. It captures the length function, but has other properties, exactly as Andy said, is locally Holder continuous, eventually positive, non-arithmetic. I'm not going to say what those are. They're important, but I'm not going to say. And then the one property I want to spend some time on is this entropy gap that we single out. And this is kind of complicated at first, so I'm going to try to go a little slow here. So the idea is that what are you worried about? You're worried that maybe your parabolic element really ruin your dynamics. Okay, that's kind of hopeless. And so you want to capture, you want to make sure that what's happening in your surface doesn't all goes through the cusps. And so, motivated by work by many people, including Shapir and Tapier, we started thinking about these entropy gaps as a way to control what happens at the cusp. And the one way to codify this is to look at a series that I'm going to talk about it in a second, and ask for this series to have finite critical exponent and diverging at S. Okay. So what is this series doing? Take your ladders and look at your function evaluated on this infinite word over all the ladders, all the words that starts with this letter A. Okay. Somehow you should think of this as a how much can you move when you start with the letter A? How much can your geodesics move when you start with the letter A? Or have to move? And if you look at it very closely, you will figure out that if you start with something that's hyperbolic, you have to move a certain amount. And so if I take e to the minus that amount, that's pretty small. Okay? So that's not going to contribute, that's not going to ruin too much my series. What might ruin my series is if when I go into the parabolic, I don't move enough. Because if my supremum is very small, then I look at e to the minus something small, that has a chance to be pretty big, and so I want to control that. Okay? So somehow, let me repeat, this complicated series is telling you that all the fun does not happen at the cusp, so you don't escape all the dynamics through the cusp. And you can encode this into finite critical exponent and divergence of the series. This is not the only entropy gap we have. There is a strong entropy gap, weak entropy gap, but for today, this is the strong one. Okay? Okay. I said it all. Nice countable Markov shifts, nice potentials. Questions? Can you move from that one? That's a good question. Okay. All right. So we have all our objects. Maybe it's time to state the theorem. The theorem holds for all topologically mixing countable Markov shifts with BIP, and all locally ordered continuous non-arithmetic, eventually positive potentials with entropy gap. Okay, all these words we've seen. Think Cusped Hitchin. And now we want to count.
Sorry, I don't get. Why do you call gap? I mean, where's the gap?
Where is the gap?
Yeah, the statement you had was just it diverges like a critical exponent, right? Why?
I think it has to do with the pressure. Yeah, I think has to do with thermodynamic formalism. Like, no?
There's a gap from 0, right?
There's a gap from 0. I don't know, why did we use gap?
It's sort of a generalization of the fact that the parabolic subgroups have critical exponent less than the entire group.
Right, but did you have the statement?
What?
No, I did not have that statement.
Okay,
but that's.
I was asking about terminology. Why is this property called the gap?
Yeah, well, it's related to a formalization of Shapiro and Tapi, and they call it entropy gap at infinity.
I mean, it's not like a gap in the sense of Sarnak.
But it is closely related to this gap between critical exponents of the peripheral subgroups.
So you mean the finiteness? You think that as the gap from the infinity? That's what you are referring to?
Well, but you also need divergence at the critical exponent too. They're both important. I think the weaker formulation is more like what you're looking for, but I forget what that is actually.
We're going to use it, but we're not going to define it. So, but we can talk later.
Geometric is the entropy gap. Geometric is the entropy gap.
Geometric is
you say, okay, it exists, it has a finite critical exponent.
Right. So what's true is that we can find the entropy as with the pressure formula. So the pressure minus this not d but delta potential. So this just Bowen's formula.
The problem is that for a countable Markov shift, the pressure isn't always defined.
Yeah.
There's this phase shift where it becomes negative and becomes.
Yeah. So if you're higher than this quantity, then your pressure is fine.
And this is going to tell you at the entropy of the representation, you're in the place, you're in the portion where the pressure is well defined. That's going to be the key point.
Yeah. So the pressure is well defined, and then this divergence tells you something about what happens when you go to df, and then if you have that convergence to minus infinity when you get close to the f from above, then you know that your pressure intersects the real axis, and so you have some Bowen formula for the entropy. But maybe I didn't answer your question. Good enough. Okay, good. We can talk later. More questions or comments? Okay. All these nice things. Maybe I need to tell you what we need to count in this setting. We used to count closed curves. Now we're going to count words that are periodic, period n, say, that have this f length at most t. And then we need to sum overall n. And then we have a little bit of overcounting. So we divide by 1 over n. And then the theorem is that there exists some numbers so that this set of periodic words, this counting, grows like e to the delta t over delta t. And the application is an Orbi counting theorem, not just for Cusped Hitchin representations, but all for annals of representations of geometrically finite function groups. So it's a little bit more general, but Cusped Hitchin is enough.
But you have not defined what do you mean by annals of representation of geometrically finite.
No, it's going to take too much. Cusped Hitchin is enough. Yeah. I mean, you should ask Dick, Andy, Fang, many people in the audience. No, yeah, Teddy. Sorry. Yeah. Okay. Good. I have 10 more minutes. That's awesome.
Okay. For each length function, you will have a special delta.
Yeah. This is yeah, you're right. I should have put a phi over there. Oh, sorry. No.
A length function.
Right. So here I just look at a potential in general, and that's why I put F.
Okay.
My F is going to depend on phi and the representation, and so this is going to be delta of F rho phi.
Okay,
Yeah, thank you. Yeah, sorry.
It wasn't known at all before, actually, the counting result for such countable, countable infinite partial shift.
I hope not, because that's the theorem. I don't know, do you?
We published it and no one yelled at us.
Yeah.
If someone else had published it first, they would have yelled at us.
I mean, it was known, as I mentioned, it was known in a certain setting, like ping pong groups.
Yeah, the Bansky and the Polyka has something similar, but in the negative curved manifolds.
Right.
But this kind of slightly different setup. But their approach might able to do the same as mine. But, yeah.
I hope not.
It'd be beautiful if there was two proofs.
All right, it's published. It's published. Yeah.
So now we can
That would be embarrassing. If someone publishes it after we publish it, that's fine.
Yeah. Okay. We're on the same.
Do you have another question?
No, but do you know the result for lambda 1 over lambda 2?
Oh, what delta is? Yeah. Ooh, I do not. Oh, no. We do. Because that's the topological entropy of a geometrically finite, also another representation of a geometrically finite function group, and then Zhang, Zimmer, and Canary proved that the entropy is 1.
Okay, good.
Yeah. Actually, we use that fact in a follow-up paper. Anything else? Okay. Again, we don't use Margulies' strategy, so I want to spend some time briefly talking about how we prove it. So this is going to be confusing. So okay, we take a nice countable Markov shift, we take a nice potential, all these things we know very well. And there's a function that you borrow from probability, meaning Lally borrows from probability a few years ago, which is called a renewal function. And so this renewal function is going to give us a foot in the door when we're trying to count. Okay, it's going to be like a way to count some subsets of the shift. So what is this renewal function? You fix a word, and then you look at all the letters in the all the words in the n preimage of x that have f length at most t, and you count them as n varies. Okay, and the important part that I didn't put here, but is that the renewal function is called the renewal function because these sets kind of renew themselves in the shift. They propagate. They have an equality that if you know one, you know the other. And the point is that if you can bound a priori this function, then you get an asymptotic behavior. Okay, so if you find a bound a priori exponentially for this function, then you know that it grows exactly like some constant e to the delta t over t delta. And so the idea is that we want to use these sets to estimate some subsets of the shift that we care about. Okay. So what sets are we going to look at? So a k-cylinder is I have words that start all with the first k letters and then they are different. And so that I call that a k-cylinder. And what we can, a little thing that you can show is that, okay, if you fix k, this is a little technical, but okay, if you fix k and you pick n big enough, then this set we really care about, so periodic word of period n that have f length at most t, actually grows like some subset of the cylinder that all have the same n image as some non-periodic word and have length at most t. And we need to look in all cylinders. Okay. And then the rough idea is that we want to apply the renewal theorem onto this subset on the right, and then we want to start partitioning into smaller and smaller cylinders, meaning k goes to infinity. So this is a strategy due to Lally, but we have a big challenge, which that this partition in the classical case was a finite partition. So if you know that some finite sums converge, you're fine. But if you have infinite sums and you need to take limits and refine, that's a challenge. And that's where a lot of work. We need to estimate a lot of subset of the shift to make sure that this happens. Okay. Ooh, I'm doing wonderfully on time. Unexpected.
Nice break.
Okay. No, I have more. Don't worry. No longer breaks.
Is it some sort of link to the shadow lemma, these cylinders and the measure the size?
Yeah, I mean, let me be careful. That's in the finite. In the finite.
Okay.
Because the alphabet here is more complicated. But yeah, so if you continue for a long path and then you diverge, there's a bound on things. Yeah. I don't know how to make it more explicit than this, though. I don't think. Yeah. Other questions?
How do you get the spectral graph?
How do we get the spectral graph? Yeah, that's involved. Right. So I guess maybe the strong entropy gap is once you have that, the spectral gap works, because what we can prove is that if you have this entropy gap, you know that the pressure when you approach this critical exponent to the right goes to minus infinity, and so then you have this entropy formula. But maybe I'm not answering your question. So.
All but finally, a really simple thing to say is that all but finally many of the terms are associated to parabolic elements. And parabolic elements are all unipotents with a single Jordan block. So, unipotents with a single Jordan block. So you can write down precisely what their Cartan projections are.
So if it's not positive, you don't know. It's open.
Oh, if the Hitchin representation is not a positive map, there is this geometrically finite condition, and so we need to change the coding a little bit. We need to use a coding of who is the coding? Dalbo et al. And then in that coding, we can code the flow using a generating set that's made all of parabolic elements. In that case, we treat the parabolic elements a little bit differently.
But even in the Iwasawa case, we're always assuming that the parabolic subgroups, which are what is responsible for all but finite elements, are at the very least weakly unipotent. And so that's essentially the same for counting purposes as being unipotent. And you just look at the Jordan block decomposition, and it gets much harder if you allow your parabolic subgroups to be Z plus Z. Then things get to be a mess, which is why this is much easier than the general relatively Iwasawa case. Yeah. But one of the reasons this is much easier than the general relatively Iwasawa.
And maybe this characterization of the cusp subgroups is due to Canary's Zimmer, so it's one of these results that we're using to run the machine. Thank you. Other questions? Okay. So maybe I'll stop after this slide. And maybe I'll show the whole slide. Okay. So there's a theorem at the top. We're going to do that last. Changing my mind. Let's start from the bottom. So we also prove an equidistribution result for these objects. And this was kind of the original motivation, actually, of the project. Because in subsequent work, same people, we use this equidistribution result and work of Canary's Zimmer to describe pressure metric on Cusped Hitchin components. That was maybe the original goal of the project. And so maybe I'll briefly say what this equidistribution result is. Essentially, you take the same setup, you have a countable Markov shift, but now you have two nice potentials that stay at bounded distance from each other. This happens for Cusped Hitchin representations. And so you can estimate the growth rate of, you can compare the G length of a word and the F length of a word, and then look at some averages, and then prove that this number grows exponentially. It's e to the delta t over delta t. And this constant is explicit, but I didn't want to write it. So this equidistribution result is proved somehow using the same techniques, but it was we then applied it to give a nice formula for the pressure metric. Okay, so maybe I'll stop. I'll skip this. There.
Thank you. Any questions that haven't been asked before?
But I know the answers to those.
So you have the coding, you have transfer operators. Why don't you prove local mixing?
I don't know. I think Nyima said, "Oh, there is this other way to do it," and we make it work. So
the motivation was pressure metric, so we wanted something analytic. That's why we
no, but he's saying you have the transfer operator, so you have that.
Yeah, that's why we.
Yeah, my impression is the Laley's method is nice, but if like the modern approach is. Unless you don't
dynamical systems people talking about modern approaches. Wow, that is amazing.
I don't know, maybe that's a joint project. Okay, maybe we can do that.
People that are afraid of the word category.
We just did what we could do.
Yeah.
We knew how to do this.
Hey, this is a conference for young people, so please go ahead. And it's a new challenge. Maybe that's, yeah, great question. Yeah.
Well, what's the your previous slide? I mean, you have minutes.
Yeah, we had an email that, well, whatever. Okay, work in progress. And maybe I'll mention you. No, I shouldn't mention you. Okay, so maybe work in progress. This is with Nyima, and work in progress means we're working on it. So there is a different counting of orbits in this setting of, let's say, Cusped Hitchin. And the idea is to take two Cusped Hitchin representations and then look when the length of these two representations are roughly the same as T gets large. Okay, and this is a first impression. Maybe it's a weird theorem to state or try to prove, but first of all, there's a precursor due to Lally in this setting of finite Markov shifts on a finite alphabet, and this has been applied to the case of closed surfaces by Schwartz and Sharp when you are hyperbolic, and by Shandai and myself to get correlation theorems about the length function of each representations. And I just really like the story of correlation numbers. So for instance, this exponent can be read off the Manhattan curve of the two potential, if you know what that is. Dai and I proved something about the correlation number that could go to 0 in tacular space, but it cannot go to 0 if we move along a cubic ray in SL3 Hitchin component. And then Polygon and Sharp proved that if you take the Hessian of this correlation number, you recover Bell-Peterson metric in a tacular space. And
so that's the analog of Francois and Richard in the closed surface case. Is that right, Francois?
A Polygon Sharp, what it did is just pressure metric. You vary the derivative of the correlation number. You can get one like scalar of pressure metric. So they did all pressure metric.
And now, since that's the question, there's also work of T and Frankie on correlation theorems, but maybe you can ask them if you want to know more. Yeah, so that's what I'm trying to work on these days. Yeah, thank you.